Hi everyone, my name is Gauri. I'm a PhD student for NTU Singapore. Today, I'm going to share with you our work done along with my collaborators. The title is shown here. Our research work focuses on few-shot learning for classification, based on exposing the model to only a few instances of the training data sample at each epoch. Numerous past and recent literatures have demonstrated promising results relative to the traditional CAM-based method. Therefore, few-shot learning research interests have risen exponentially in current times. Prior works in few-shot commonly utilize learning of degrees of similarity between images using a distance measure for class labeling, whereby similar images are assigned to same class label, while vastly dissimilar objects are placed in different class labels. This can be done via two approaches. Either through computing such similarity in the image feature directly, as in Siamese network, or embedding the features into higher dimensional spaces, as in prototypical network. The embedding, if it's done, consider the visual features as individual points in the higher dimensional space, in which a pictorial representation for three-class setting is shown on the right. Although state-of-the-art classification performances have been reported, there are certain limitations. The first is that the point estimation as described may be inaccurate under unevenly distributed limited support sample. The second is that if there are any inconsistency in the data distribution between the train and test phase, overfitting may occur. Lastly, using only a single feature point lacks interpretability and is insufficient to indicate a class, which is highlighted over here. Therefore, distribution-based approaches have been proposed to mitigate the limitations. Once again, a pictorial representation is shown on the right. However, an intractable integral remains to be computed if one opts for a probability distribution computation, and thus a variational approximation can be invoked. Most, if not all, existing work involve minimizing a Kullback-Leibler divergence. However, we noted the existence of other possible but related distance measures such as the HELlinger distance. So, why the HELlinger distance? There are a few reasons behind this choice. The first is that the HELlinger distance is the probabilistic analog of the Euclidean distance, and thus making any computation more straightforward than that of the KL divergence. The second is that we do not need to worry about its value diverging to infinity when any input distribution value tends to 0 during the computational workflow. Lastly, there are works that exist on using the HELlinger distance in other domains, for instance, in audio classification, but as far as we know, there are little focus on using the distance for few-shot image classification. Moreover, we also stress the importance of attention mechanism in few-shot learning. The significance lies in that it allows the model to focus on essential visual features and omit irrelevant ones, which increase the efficiency of the model. Also, existing few-shot words, which are not variational approximation based, utilizing attention are of wide variety. Some examples are shown over here. All such models have reported improvement in the classification score via the respective ablation studies. As far as we know, there are fewer works that exist on variational few-shot attention-based classification. The closest we have is cited as here, but the work considered KL divergence instead of HELlinger. Therefore, we propose the HELA-VFA, the full form is described over here, which contain the following novelties. Firstly, we pioneered the HELlinger distance-based feature aggregation for few-shot variational learning. Secondly, we improved upon the VFA net via introducing the attention mechanism during the feature extraction pipeline. Lastly, we also introduced the HELlinger similarity loss, amalgamating it with categorical cost entropy and the reconstruction loss. Here, we illustrate the algorithmic pipeline of our proposed model, and we will start by focusing on the attention mechanism component, which comprises of both China and spatial attention modules. For the China attention, we extracted the intermediate feature maps via both average and max pooling. The obtained features are then processed by a multi-layer perception layer with the mathematical operation defined as shown. We note that the sigma here represents the sigmoid derivation function. For the spatial attention, the max and average pooling were utilized again, but the features are now concatenated along the China axis instead. We then apply a 2D convolutional layer with filter size of 7 to compute the resulting attention map as illustrated by the mathematical formula here. The features from China and spatial attention components are combined in the following manner, whereby the cross symbol here represents the outer product between the extracted features and the attention maps. The next big component I want to talk about is obviously the HELlinger distance. turns out that we can derive a modified form of the evidence lower bound, ELBO short, in terms of the evidence term and the divergence measure for the Hellinger distance. Full derivation is shown in our paper. In this slide, we merely state the result. The original definition of the ELBO and the respective distribution required are also shown here. So we use a KL divergence ELBO as comparison. So we note that the KL divergence ranges from 0 to infinity, while the term containing the Hellinger distance measure ranges from negative infinity to 0. Despite the differences in the mathematical form of the two ELBOs, one thing remains common. When two conditional distributions, which I mean the prior, the P here, and the posterior, the Q here, equates to one another, both distance measures become 0. This means that the modified ELBO, or the ELBO for the KL divergence, will be equals to the evidence term. This also means that maximizing the respective ELBOs is the same as maximizing the evidence term for both cases. The last component you want to talk about is the Hellinger similarity loss, mathematically defined as shown. The respective terms in the equation are also described in this slide. One thing to note is that this loss function takes on a somewhat similar form as that of the cosine similarity softmax loss used in image classification, which is true to an extent. So the reason why we propose this loss because we are inspired by cosine similarity softmax loss. So for our loss function, we replace the cosine similarity with that of the Hellinger similarity. Such reason for the replacement is already described in this slide over here, and we also have mentioned it in the previous slide. So to sum up, the total loss function of our HELA-VFA is as shown here, whereby lambda 1 and lambda 2 represent the weight parameters. So here, we illustrate the experimental setting using these 4 benchmark datasets, in which C5FS and HE100 are derived from the C500 dataset, and the mini ImageNet and tier ImageNet are all derived from the ImageNet dataset. The meta-train, valid, and test class are as shown here. All simulation conducted using PyTorch and following the standard few shot literatures, we adopt the n-way one-shot and n-way five-shot strategies. So we choose the number of class n to be 5 in our evaluation. Adam gradient descent optimization were used with a learning rate of 1 times 10 to the power minus 3. The batch size and epoch are also shown here. So we depict some numerical results for our approach relative to the state-of-the-art approaches as shown on these tables. For more information, refer to our paper. All CNN backbone utilized for the state-of-the-art are ResNet 12, except for the SO online we utilize a ResNet 18 backbone. So we see that our method consistently outperforms that of the state-of-the-art in both 5-way one-shot and 5-way five-shot evaluation in general. Such trend is brought over to the mini ImageNet and tier ImageNet evaluation. Except for the 5-way one-shot tier ImageNet, you can see over here that the IER distill actually outperform our method, but only by a small percentage, around 0.28%. So we have also seen that for 5-way one-shot approaches, the value that's obtained is usually less than that compared to 5-way five-shot approaches. This is because by using lesser shot, or you are exposing the model to lesser number of image sample, and this may be hard for the image to actually learn more useful feature for easier generalization to more image classes. So lastly, when we talk about the ablation analysis, it's actually important as it elucidates empirically the role of each number components on the classification performances. So we see from the tables that in both datasets, utilizing both attention and Hellinger components yield the optimal classification score consistently. So this emphasizes the importance of these two components in our classification scores. The value decreases gradually as each of the novel components got removed. And throughout the analysis, we have found that utilizing the Hellinger distance will yield better results than that compared to the KL divergence. So with that, we conclude our presentation with the various points that we described extensively summarized in these slides. Lastly, thank you for your attention, and we thank the Air Traffic Management Research Institute and the Civil Aviation Authority of Singapore for supporting this research project.